Swayam Prabha. Digital India. Educated India.
Good morning all of you, and welcome to the last lecture of this course. Most of you must have been quite happy and relieved also that you have to go through a lot of assignments, I know, and also computer assignments as well as detailed derivations, probably putting a lot of effort compared to the other 3 credit course, but this is a course where you learn by applying, So, I mean, the classroom lectures are just kind of helping you to understand in a broader sense, but as long as you solve a particular problem yourself, you will not be understanding, because we have so many different types of problems in convective heat transfer. It is not a one particular type of solution and then you just change the boundary conditions and then you find different equation solutions and so on. So, we have external flows where we have a particular type of solution, and then internal flows altogether again different regimes. You see how, so it ends up from starting from a simple integral equation all the way to solving a PDE, anything we can do within the internal flows. Okay. And again, when we are talking about natural convection, again the solution methodology changes, because you have coupling of heat and mass transfer, right. So, then we same method, the approximate solution, or for example the similarity solution, when we apply it to natural convection has to be slightly modified, the kind of unknowns that we are dealing with. Again, when you talk about turbulence, it is altogether different. It looks way different from the kind of analysis we have applied to the laminar boundary layer equations. We have not looked at any similarity solutions in turbulent flows. So, whatever was possible in terms of simple analogies, we have been trying to derive. So, in that sense this course convective heat transfer has lot of things to be covered, so it's quite a bit of challenge for me also, and to make justice to this course. Still, in spite of that, we have not covered topics like porous media, convection in porous media, then we have phase change, condensation and boiling. So, these are also parts of really speaking convective heat transfer, but I would suggest that we, since in our department we are also offering specific courses related to those topics, such as boiling and condensation, porous media. So, anybody who has taken this course now should be able to easily get along with those courses as well, because the foundation has been very well established. So, the rigor will be more or less similar, it is only you are just changing the approach a little bit when you do it for porous media, for example. Okay, you have additional resistances which have to be counted for. Boiling and condensation is also highly empirical subject. So, the kind of analytical solutions are very limited to extremely simple cases, especially in condensation. In case of boiling, you cannot find any analytical solution. More or less everything has to be empirically, there is not even a rigorous derivation, but the thing is the physics of boiling is very complex. So, there is a combined heat and mass transfer. So far we have not looked at mass transfer in this course. Again, when we say convective heat, it is also convective heat and mass transfer. There are cases where mass transfer is an analogy to heat transfer, just like we are doing an analogy between heat and momentum through Reynolds, Prandtl, all these analogies. So, we are solving the flow field and finding the heat transfer solution. Same way we can also find an analogy between heat transfer and mass transfer. So, we introduce another non-dimensional number called the Schmidt number. which is the ratio of momentum to mass diffusivity. And once we know this, then once you know momentum diffusivity, you can extract the mass diffusivity, and a similar kind of analysis, instead of Nusselt number we define a Sherwood number, things like that, mass transfer coefficient instead of heat transfer coefficient. So, it becomes very similar. Instead of Prandtl number, you have a Schmidt number which becomes the governing parameter there. But there are cases where the heat and mass transfer gets coupled. That is, a good example is the phase change, evaporation for example. So, in evaporation you also remove certain amount of mass from one phase and add it to the other phase. So, that becomes more complex. Now, when you couple heat and mass transfer, you cannot find analytical solutions again. So, that requires a very rigorous treatment. Even numerical solutions are kind of hand waving approaches, whatever we have in a commercial computational fluid dynamics packages and so on. So, they are not very rigorously established models, and we are still elusive. Okay. So, I mean so boiling and condensation in that sense it is a highly empirical subject. You have to deal with a lot of correlations and experiments which have been conducted and the understandings of that. Okay. So, yeah, overall this is a very vast course, So, I think it is really hard to cover all these topics in one semester, if at all can be done, but it can be done, but you will not be able to appreciate the depth of this subject, So, which I think already most of you are aware of the breadth of this course. So, when you take a heat transfer course, I am sure you are exposed to the breadth of heat transfer, but unless you probe deep into a particular topic, you will not be able to appreciate the fine aspects of finding rigorous solutions, especially analytical solutions. Okay. So, when it comes to turbulence, again people have different approaches to it. My personal approach is also, I do not look for analytical solutions everywhere, but you should understand that for certain problems there are analytical solutions available which you should not overlook. Okay. For example, I have seen cases where people solve the flat plate boundary layer numerically and they do not know where to look for the Blassier solution to validate. Okay. So, you should know by now for which cases you can actually compare with exact solutions. Even when you talk about turbulent flat plate boundary layer, so we have correlations derived from approximate methods. Okay. In the last class I was talking about the use of analogy, Reynolds analogy. So, in that case we have established an empirical relation for the skin friction coefficient, right. So, if you remember what was the relation for CF. So, this is an empirical one. Okay. This we cannot rigorously derive this. Okay. This is coming from set of experiments, okay, for the hydrodynamics part. Do you remember what this correlation is? 0.046 into, now when we define RE, now rather than defining it as RE, because RE you might actually misinterpret the length scale used. So, here it is whatever UM or U infinity depending on whether this is an external or internal flow. If you are dealing with external flow, you have U infinity and then the length scale is now the boundary layer thickness divided by mu. What is the minus 0.2. So, this is a kind of most commonly used relationship. For internal flows it becomes easier, you replace your delta with D, right, and then the next step is, if suppose you take the case of internal flows, the simplest analogy that we have derived so far is the Reynolds analogy, right, which considers the entire boundary layer to be purely turbulent. Okay. So, for this case Reynolds analogy, what does it say? Your Stanton number is equal to Cf by 2. For this, in this case you are actually neglecting the role of molecular diffusivities compared to the turbulent diffusivity, which you know that for there is an influence of molecular Prandtl number even in the turbulent Nusselt number case, because this is a wall phenomena and near the wall the molecular diffusivities cannot be neglected, right. So, therefore, Colburn extended this Reynolds analogy to also cases where he considers the effect of molecular Prandtl number, okay. Then it becomes the Reynolds Colburn analogy, and what does it say? Your Stanton number times PR power 2 by 3 is equal to Cf by 2. Now, when we substitute the expression for Cf into this, therefore, we find we can derive an expression for the Nusselt number. Do you remember what it is? 0.023 times RED power 0.8 PR power 0.3. Okay. So, this is called the Ditus bolt. Ditus Boulter. Okay. So, Ditus Boulter correlation, many people think it is a completely based on empirical formulation. It is semi empirical. You can say that this skin friction coefficient is empirical, but after that we use the Reynolds analogy to get this. And again in the textbooks there is a variation of exponent of Prandtl number. For heating we use value, cooling we use 0.4. So, but it does not matter, overall the structure of this comes from the Reynolds analogy. Okay. So, then it has been slightly modified depending on the heating or cooling case, because the Prandtl number dependence is not a very exact dependence. It has been introduced later on by Colburn, but it depends whether you have a heating or cooling. There has been shown to be a slight difference, but not too much. Okay. Some people use an average value of 0.33 and they are still okay with that, right. So, now for the external flows, however, you have in terms of the boundary layer thickness delta, right, which has to be first determined, because we know that in the external flows boundary layer thickness delta itself is a function of Reynolds number. So, therefore, we cannot simply define Reynolds number based on delta and stop here. So, we have to, therefore, how do we do this? We have to use the approximate methods. Okay. So, the only way to find delta as a function of the local Reynolds number is to use the approximate methods and then substitute this for the wall shear stress, and then we will have an expression for delta, and then we apply the Reynolds analogy, then we find the Nusselt number correlation. So, there also you will have something similar, except that this constant gets slightly modified and the Reynolds number dependence still remains the same, only this becomes a local Reynolds number, okay, and the Nusselt number also becomes a local Nusselt number. Because in the external flows your boundary layer thickness keeps varying. So, therefore, the Nusselt number and Reynolds number have to be defined based on the local coordinate. Okay. So, from this you can understand even for internal flows, in the laminar case your Nusselt number was constant in the fully developed region, but what this says is that even if it is fully developed in the turbulent flow, this is still a function of Reynolds number and Prandtl number, correct, because what is fully developed? It is only the turbulent boundary layer. When you say these two boundary layers, these are the turbulent boundary layers. So, only these are merging, but the viscous sublayer will not merge. This is very close to the wall, it will not merge. Okay. So, therefore, there is an influence of Reynolds number now, because Reynolds number controls the amount of this viscous sublayer thickness, okay, which in turn affects your Nusselt number. So, although your turbulent boundary layers are fully merged, your viscous sublayer is still remaining, which is now governed by the value of Reynolds number, and therefore, that comes into the expression. And so is the case. Now, since this is a heat transfer case, Prandtl number will also be important. Okay. So, please remember that in the turbulent fully developed flow, you do not have a constant value of Nusselt number like in the laminar case. The laminar case does not depend on Reynolds and Prandtl number, because you have only laminar boundary layer. Once it is merged, there is no effect of what you are putting upstream. Whatever Reynolds number may be, once the two boundary layers are merged, you will have the same profiles, and only thing that will decide the Nusselt number will be boundary condition, whether it is a constant wall temperature or constant heat flux. Only that alters the nature of the temperature profile, whereas in the turbulent case, still this is dictated by the Reynolds and Prandtl numbers. Okay. So, this is a very popular correlation, you know. So, you find in most of the engineering applications, people use the Dittus-Boelter correlation without having to worry what is the accuracy of this, how it has been derived, and still it gives a reasonably good prediction within something like plus or minus 15 to 20% of the experimental data, right. So, within for simple flows like pipe flows, you know, flat plate boundary layers, the people have been successfully using this, right. For more complex flows, they have to look at numerical solutions. There is also we should however, you know, we should look at modification to the basic analogy. Okay. We know that although this is a very useful analogy, widely used, but nevertheless, since this considers the entire boundary layer as turbulent, it is not the most accurate representation of the turbulent boundary layer profile. So, we have seen that that the entire turbulent boundary layer profile can be divided into 3 regions. So, if you plot u plus and y plus on a log scale, for example, right. So, for example, if you are talking about, so you have 5 here, you have something like 50, let us say you have 100, let us say this is like 500 and so on. So, based on this we have identified a profile in the viscous sublayer which is linear, plotted on a logarithmic x axis becomes a curve like this. Okay. So, and then we have another expression for the log layer which is extending above y plus of 30. Okay. So, that can actually, if you extend it, it goes something like this. Okay. And here it is given as a logarithmic profile. So, do you remember how the profile looks? Plus a constant, and this is your von Karman constant which is 0.41 and this is 5.5. Okay. These two we have derived from the basics. Okay. Now, also there is a patching layer which has to be connected between the linear and the logarithmic variation, another logarithmic profile. So, this is called the buffer layer. Okay. So, also represented with a logarithmic variation. You remember what the profile is? 5 y plus minus 3.05 So, this is your buffer layer. So, this is valid for y plus greater than 5 less than 30, right. This is valid for y plus less than 5 and this is valid for y plus greater than 30. These are all kind of, you can really measure the viscous sublayer and the log layer very clearly. Okay, when you have a very fine probe which can resolve the viscous sublayer, you can actually measure and show that the data also falls with these. So, this has been generally well accepted. Again, variations will happen when you have pressure gradients, whether when you have flow separation, okay, then when the boundary layer itself is detached. So, then this kind of profiles will not be there. So, according to the Reynolds analogy, we altogether neglect this and only consider the entire turbulent log law profile, okay, and then we make use of the calculations of turbulent wall shear stress and also the heat flux, everything to be having only one component which is nothing but the turbulent diffusivities. We integrate it all the way from the wall to the edge of the boundary layer, okay. We ignore completely the molecular diffusion and then we derive the Reynolds analogy. So, naturally an extension to this is called Prandtl-Taylor. So, I am not really sure about who really did it, but looks like it has been also named after G.I. Taylor. So, it should have been I think maybe a joint kind of intuitive discovery of both Prandtl and Taylor. So, it has been credited to both of them. So, in this case the point is that we assume a two layer model where the inner layer, which is the viscous sublayer, is also considered, which is the important thing. The molecular diffusion has to be dominant near the wall, it cannot be ignored. So, therefore, we consider the viscous sublayer and we consider the rest of the boundary layer to be turbulent. So, when we draw the velocity, for example, as a function of y and also the temperature. So, we will have a variation like this, for example. So, till a certain location, so let me give it a much yes, okay. So, till a certain location, this will be dominated by viscous effects from the wall, and from this point let us call this UL, where it transitions from a laminar sublayer to a fully turbulent layer, okay. The corresponding thickness of the viscous sublayer, let us call this as delta L, okay. So, above this the profile becomes governed by fully turbulent diffusivity, right, and finally at the edge of the turbulent boundary layer, okay. So, you reach the velocity which is either the mean velocity inside the duct or it is a free stream velocity in the external flows, okay. So, this is at delta, right. So, therefore, now you have two regions, one is your viscous sublayer and the other is your turbulent boundary layer. Similarly, if you draw the temperature profile, something like this. So, your temperature profile is governed by, again let us say till up to the laminar sublayer you have a value which we will call TL, okay, and from that it becomes fully turbulent, and then outside it reaches the value Tm. So, this is your temperature variation with y and this is your velocity variation with y. So, this is the picture of a two layer model which was used by Prandtl to derive the two layer analogy. So, naturally the assumption here is that we are picturing the entire within the turbulent boundary layer is divided into two layers. Okay, one is the viscous sublayer near the wall and we have the turbulent boundary layer outside. Okay. And again when we derive it, we also use condition that turbulent Prandtl number is equal to 1. So, when we say turbulent Prandtl number is equal to 1, we say that your delta is equal to delta t, okay, because even though if you assume turbulent Prandtl number is equal to 1, all the processes at the wall are governed by the molecular diffusion. Okay. So, therefore, the assumption of delta t is equal to delta outside will not affect what is happening near the wall. Okay. So, the same thing is also used in the Reynolds analogy, right. So, in the Reynolds-Colburn analogy also we use turbulent Prandtl number equal to 1 and then only we derive the analogy. Okay. So, the assumption is that inherently this is not bad, and especially when we are doing even turbulence modeling, most of the time we assume this turbulent Prandtl number to be close to 1. Okay. So, the starting point of this is now we have the shear stress which has now both the molecular and the turbulent diffusivities. So, we can write this as mu plus mu t into du by dy, and similarly the heat flux also consists of minus k plus kt dt by dy. Okay. So, if you are looking at Reynolds analogy, it assumes fully turbulent. So, therefore, we neglected mu compared to mu t, k compared to kt, and then we we integrated from the wall to the boundary layer and then divided one over the other, and then we ended up with this. So, now we have divided this into two regions. So, we will first apply this for region 1, which is the laminar viscous sublayer. Okay. So, within the laminar sublayer, can you integrate, let us say equations 1 and 2 within the laminar sublayer, where we can neglect the turbulent diffusivities, integrate your velocity and temperature profiles from your wall till the edge of the laminar sublayer delta I. And then take the ratio of 2 by 1. So, that is the heat flux divided by shear stress. First integrate it and then you divide it. So, what do you get if you do that? What will happen to tau? So, at wall it becomes tau wall, right, and this is mu t is neglected, you have mu, and then the u gets integrated from 0 all the way to ul, okay, and y all the way from 0 to delta L. The same way here also you have q wall, and this gets integrated from t wall to TL, and then this is also 0 to delta L, and then we divide 2 by 1. So, delta L gets cancelled. So, essentially we will have therefore q wall divided by tau wall is equal to minus k by mu into TL minus T wall by UL. Okay. So, therefore, we can write this in terms of molecular Prandtl number, multiply and divide by Cp. So, mu Cp by K. So, we can therefore write this as Cp divided by Prandtl number. Okay. So, let me call this as equation number 3. So, now next we will apply equations 1 and 2 in the turbulent boundary layer. Okay. So, for turbulent boundary layer, we can of course do the other approximation where the turbulent diffusivities are much larger than the molecular diffusivities, okay, and therefore we can integrate from delta L all the way till delta, right. So, you do the integration of these profiles from delta L all the way till delta and then divide again 2 by 1. Okay, let us see what is the expression that you get. So, let us say again you have q double prime by tau will be equal to minus Cp into Tm minus TL divided by Prandtl number into Um. So, where do you have Prandtl number here, because this is turbulent. So, this is PRT is equal to 1. So, therefore, we can write it. So, therefore, now we have this is your equation number 4. So, for continuity the same wall shear stress or wall heat flux has to be taken all the way from the wall to the edge of the turbulent boundary layer, correct. So, we are right now assuming a one dimensional transport of heat. So, whatever you apply at the wall has to be transported all the way till the edge of the boundary layer. So, therefore, this has to be the same as the wall quantities here, correct. There is no discontinuity in the heat flux or shear stress. Will also be felt by the turbulent boundary layer, same with the wall shear stress. Okay. So, therefore, we can just replace q and tau with q wall and tau wall, and now the unknown quantity in this, we know, for example, for a given isothermal condition we know what is the wall temperature T wall, okay, but what we do not know here is TL, the temperature at the edge of the laminar sublayer. Okay. Now, UL is also obtained from measurements, okay, we will see how do we get it, but when we are solving the heat transfer problem TL is difficult to obtain. So, therefore, we will eliminate TL by using these two equations. So, therefore, eliminating TL between 3 and 4. So, how do we do that? We just add 3 plus 4. So, if you add 3 plus 4, you have minus Cp, you have plus CpTL, there you have minus CpTL. So, the TL gets eliminated right away. Okay. So, therefore, you please do 3 plus 4. If you do that, so you will be ending up with the following expression, which is q wall double prime by Okay. So, I just take this to the left hand side, okay, and then this also to the left hand side, and then I add 3 and 4. So, on the right hand side I have Cp into T wall minus Tm. Okay. So, this is, let us say, equation number 5. In this case the TL is eliminated. So, what I ask you to do, now that we have something like Q wall by tau wall, okay, you can take this tau wall to the right hand side and write this in terms of Stanton number. Okay. So, if you write this in terms, that means Q wall by T wall minus Tm is nothing but H by rho Cp into Um is your Stanton number. So, write this in terms of Stanton number on the left hand side, take the other extra terms to the right hand side and see what kind of expression you get. Okay. So, you should be able to get an expression for Stanton number is equal to function of the other terms including Prandtl number. So, now this entire term here is Stanton number. So, Q wall by T wall minus Tm is H divided by rho Cp Um. Okay. So, your Stanton number therefore is equal to, now what I am going to do is multiply and divide by Okay. So, therefore, I will have tau wall by rho square is nothing but your Cf by 2. Okay. So, this is your Cf by 2, and when you take common, so you have Prandtl number into Ul by correct, plus I have, I will just rewrite it, one plus Ul by into Prandtl number minus 1. So, finally, I end up with a relation between Stanton number and Cf, and you see in this case naturally the Prandtl number is coming. So, I am not forcing Prandtl number to come in like the case of Reynolds-Colburn analogy. Since we have not neglected the viscous sublayer, we have also considered that. So, naturally the Prandtl number is built in inside this analogy, right. So, now the only thing that needs to be closed is Ul by So, Ul by actually is measured for turbulent flows, turbulent boundary layers, and we have some correlations for that. Now, let us see for the case of a circular duct, for example. So, the Ul by is expressed as a function of the Cf, written as 5 into square root of 1 by 2 Cf. So, this is the kind of correlation. Okay, let us call this as equation number 6 and this is number 7. So, if you plug in equation 7 into 6, so you get the expression for a circular duct, you get the analogy Cf by 2 divided by 1 plus 5 times Cf again into Prandtl number minus 1. For example, so this is the analogy for the circular duct. Similarly, if you are talking about maybe a rectangular duct, you will have a different relation between Ul by and Cf, which you will substitute and get the final analogy. Okay. So, therefore, once you know the CF, we can use the previous CF that we have written down, okay, for the Reynolds analogy, that can be used substituted here, and we can find an expression for Nusselt number, right. So, this is how the Prandtl-Taylor analogy is developed. So, for the case limiting case where Prandtl number equal to 1, so where we have a fluid which is having a Prandtl number exactly equal to 1, the molecular laminar and thermal diffusivities are identical. So, what happens to this? Reduces to the Reynolds analogy. So, in this case, this gives you that Stanton number is equal to. So, you see that Reynolds analogy is not bad after all, especially when your Prandtl number is equal to 1, that is your molecular Prandtl number equal to 1. Reynolds analogy is the correct analogy, because all the complex analogies are finally collapsing to that. Okay. It only makes a difference where your molecular Prandtl number is either very large or very small, that is when you start deviating from the accurate results. So, most of the gases you do not have to worry. So, you can actually, therefore, most of the gases you will find Reynolds analogy it is reasonably accurate, whereas if you apply it to very large Prandtl numbers or very small Prandtl number, liquid metals and so on, very small Prandtl numbers. So, then you will find that Prandtl analogy is more accurate than Reynolds analogy. Is that clear? So, this is more complex expression naturally. So, the final case will be to consider all 3 layers including the buffer layer, right. So, if you also consider the buffer layer, then you are tracking the transition more accurately. So, I will not derive that, but I will only give you the final analogy. So, this 3 layer analogy is called the von Karman analogy. So, finally, the most complex analogy that you can derive. So, this is based on the 3 layer model, which includes the laminar, the fully turbulent and the buffer layer, and this case the expression for the final expression for Stanton number for the case of circular duct. Okay. So, you have the same term till now this is the same as the Prandtl-Taylor analogy. Okay. Now, the additional term comes because of the buffer layer. So, this additional term is coming in due to the buffer layer. Okay. So, this is the difference between the 2 analogies, and again for the limiting case of Prandtl number equal to 1, what happens? Same, this becomes 6 by 6, so ln of 1 0, this again becomes 0, so you have Cf by 2. So, finally, it collapses to the Reynolds analogy again, right. So, for more complex cases where none of these analogies will work, okay, so we cannot find a simple analytical solution, again then we have to use numerical solutions for heat transfer. Okay. So, we will kind of stop here because although turbulent heat transfer involves lot of modeling, I do not want to talk about in detail because these are covered in other courses related to turbulence modeling and so on, where you can learn how to use different models for different problems, and they are also available in many of the numerical solvers. Okay. So, you can also go through those documentations, try to understand which kind of turbulence model work for different kinds of problems. Now, practically when you are working with turbulence, you will not be using too much of analogies. So, most of the complex engineering problems cannot be solved with analogies. So, there you have to find numerical solution. So, you will be using some kind of turbulence model, right. Okay, so, we will I hope that I could cover with the limited number of hours at least some overview about turbulent heat transfer. Okay, thank you so much.